Hello, good afternoon. My name is Miguel. Salinas. I'm going to be talking about the molecule selenocysteine. The introduction for selenocysteine. Selenocysteine is a special amino acid found in some proteins that help protect the body from damage. It has three main parts, which is a carboxylic acid, an amine group, and a seleno group. These parts allow it to form hydrogen bonds and dissolve it well in water. In the IR spectrum, we can see peaks that match each of these groups, helping confirm the molecule structure. This makes infrared spectroscopy useful in studying and identifying selenocysteine. And as we mentioned, we have a seleno group right here with the HSE. We then have an amine group with the NH2 connected to the chiral. Then on this side, on the right side, we have a carboxylic acid. So we have the Lewis structure for this, which is drawn out. The Se has lone pairs. The N has a lone pair. C double bond O has lone pairs. And this OH has two lone pairs. Now we have the line angle structure. So if you ever see a molecule with a wedge like this, especially at the chiral, this tells you that there is a hydrogen right here. And this hydrogen, just because this has a wedge, this hydrogen is going to be a dash. And later on in the slides, we're going to find out why this molecule of selenocysteine has a R configuration. So the molecular formula for selenocysteine is C3H7NO2SE. And this carbon right here that I'm pointing at, we have a paramate carbon because it is connected to one carbon, which is actually the chiral. It is a paramate carbon, which is sp3, 109.5 degrees, and a tetrahedral. Reason why it's sp3 because there are two hydrogens that are here. You cannot see them, but they are connected to basically make the carbon happy with the octet rule. Then for the seleno group, we have sp3. It has the single bond to the C, single bond to the H, and it has two lone pairs on top of the C, or one on top of the C and one below the SE. The SE. So we then have a secondary carbon, which is a chiral. It's connected to one carbon on top to the top of it, and a second carbon right below it to the right. Now right here, we have a primary amine because it is connected to one carbon. Then we have sp3, 107.5 degrees, and trigonal pyramidal. Reason why it's not 109.5 is because it has a lone pair. And whenever you have a lone pair on basically on an atom, you must take away two. So this lone pair made it have 107.5. This other carbon right here is a primary because it's connected to one, the chiral carbon. This whole section right here is a carboxylic acid. It has a sp2, 120 degrees, and trigonal planar. A double bond right here is considered 1. This single bond to the chiral is 1. And this single bond to the O is 1, meaning it's sp2. And this double bond O is S, lone pair here, lone pair to the right of it is sp1, p2. And lastly, this OH has two lone pairs, which is sp1, lone pair sp2, another lone pair sp3. Has two lone pairs, which is why it's 105.5 degrees with a bent shape. Next, we have resonance. So there's only resonance on this side of the molecule, where the lone pair becomes a double bond, and this double bond becomes a lone pair up here, which is why it will get a negative. And to the top of it, since we know that oxygen has 6 electrons, now it has 5. 1, 2, 3, 4, 5. which means it lost an electron, which means it makes the oxygen positive. And this double bond came up here, which gives it an extra carbon. It has 7 carbons. It has 7 electrons. It has 7 electrons, which is more than what it should have, which gives it the negative right here. So this one has 5 electrons, and then this one has 7 electrons. Next we have the functional groups, which is seleno, primary amine, carboxylic acid, which was mentioned earlier. It has hydrogen bonding with the HSE, NH, and OH. Dipole because it has lone pairs, which makes it polar. London dispersion forces, as we mentioned, has dipole moments in NH, OH, SEH, and the C double bond O. And just because it has all these hydrogen bonds, it makes it very soluble in water. Next we have the pKa's of these functional groups. So the first one is COOH, which has a pKa of 2.2, which makes it a weak acid. SEH with a pKa of 5.2, which makes it a weak acid. NH2 with a pKa of 8.3, which makes it a weak base. So the C double bond O minus accepts or donates the H plus, the Se minus donates the H, and the NH3 accepts the H plus. So in this case, we have Lewis bases and Lewis acids. The ones with the lone pairs are the Lewis bases. And in this case, this one is a Lewis acid as well, a Lewis base. And in this case as well, the C double bond O is a Lewis acid, which in some cases they can be both Lewis acids and Lewis bases. Now we see why we get the R. So you must number these basically from biggest to smallest, depending on how it looks and what it's connected to. So this chiral right here in the middle is connected to straight to the N, which makes it 1. This carbon is connected to an Se, which makes it 2. Then this carbon would make it, or this side of the functional, or this side of the molecule, which is a functional group of carboxylic acid, would make it 3. So in this case, it would be 1, 2, 3 for the carboxylic acid. And the fourth one, as you mentioned, is a invisible hydrogen with a dash, will be 4. So it's 1, 2, 3 in a clockwise way, which means if the H is on the dash or the fourth smallest one is on the dash, it stays the same. It does not need to flip, which is why it gives it the R. And the 2 is because it's on the second carbon. And also on the second carbon, we have the amino group, which is the amine right here. And on the third carbon, we have selenopropanoic. We have the seleno group, which then becomes the propyl, which is right here, the 3 carbons. And the reason why it says oic is because of carboxylic acid. And as I mentioned down here, the carboxylic acid makes it have the oic ending. Then we have the reasons how we got the R, which I mentioned before. And a way to get the enantiomer, is to basically do the opposite of what it is. Make the wedge into a dash and make the dash into a wedge. And there's no diastereomer, there's only one enantiomer for this case. And the Fischer projection is another way to basically show how you get the R group. We said that NH2 was 1, SEH was 2, COOH was 3, and in this case it's going to it has a counterclockwise. But you must know the ones on the horizontal line, like the H, it basically has a wedge. It has a wedge. So whenever you have a wedge, especially when the fourth one is on a wedge, you must flip it. You must flip the configuration. So we know that a counterclockwise is an S, and just because the H is on a wedge here on the horizontal line, it must flip it, which is why it has an R. Now we have the nucleophilic ones and the electrophilic. So the nucleophilic ones are the ones with the lone pairs, as we can see here. And the ones being pulled towards it are the electrophilic ones. That's why we see H, C, and H are less electronegative than the N. And this O, the bond O, pulls the C towards it because it's more electronegative than the C. And H and C are less than the O, which is why you see those arrows pointing towards the O. So now we have the synthetic routes to the molecule. We start off with biosynthesis, which is an enzyme mediated on the tRNA seq, and is used for in vivo protein synthesis. We then have serine conversion, which is the OH converts to SEH via substitution, and is used for lab synthesis of free seq. Then we have SPPS, where the protected seq inserted into peptides, and is used for peptide/protein synthesis. Then we have chapter 6, where it shows the biochemical reactions of the molecule. So in this case, it has a redox reaction where the selenium group is a highly reactive reaction and can be oxidized and reduced easily. The SE negative form of selenocysteine makes this actually a strong nucleophile or nucleophile, which is very effective in a catalyst, and this is called a nucleophilic catalyst. Medical importance of the molecule of selenocysteine is that it protects cells from oxidative damage, maintains cellular redox balance, and is involved in thyroid hormone metabolism and helps prevent oxidative stress-related diseases. And one of those diseases are heart disease, which makes us think that maybe, or actually, selenocysteine is very important to this world if it is actually protecting people from diseases like heart disease. So it actually does have a great importance in the medical field. And now we have the IR spectrum. So whenever it comes to looking at the IR spectrum, you're going to see that it has different types of peaks. And these peaks that you can see here basically explain what it has. It can have a C double bond O, a CH, an OH. Just depends on what type of molecule it is. So in this case, right around the 1700 mark, we have a C double bond O, which is connected to NH2 and a functional group. And whenever you see R, that just means it has a functional group. Next, we have a carboxylic OH acid, which it starts around 2100 and ends about almost 2800. And you can see here it's very wide. This starts off very wide and not very sharp like this one. And when it's very wide like this, and especially in this type of range, then this would tell us that it has a carboxylic acid, which has an OH. And in this case, we have a peak around 2900, which tells us it has a CH. Importance and conclusion. The importance of selenocysteine is that in the future, it could be used to solve more problems with people health-wise. So as we mentioned before, it is used for diseases like heart disease. So in my opinion, I feel like if we put in more time, research, and money into this molecule, then maybe it can solve more problems when it comes to diseases. More research can, open the doors to a lot more opportunities, for medical science, especially to help people around the world. So there are still a lot of discoveries that are yet to be found with selenocysteine, but as of now, it is very helpful when it comes to diseases and helps prevent a lot of things that can be fatal. And that is it. Thank you.